Good day, everyone. This is Dan Day from the Princeton University Office of Communications. I'm speaking to you from the main campus, while meanwhile, out at the Princeton Plasma Physics Laboratory, a couple of miles away, are two of our colleagues who are about to show you the remote glow discharge experiment, a physics and plasma experiment that you can do from your home or your school or your office or wherever you have an internet connection. The Princeton Plasma Physics Lab is a Department of Energy laboratory, a national laboratory managed by Princeton University and staffed by scientists who are working with other scientists around the globe to develop fusion energy. Fusion energy is a potentially new, clean, safe, and abundant supply of energy that could be used to power our homes, our offices, our cities, and our nations. There's a lot of work going on around the world, and a lot of it is happening at the Plasma Lab. Our scientists there have developed an unusual experiment in that you can access it from anywhere you have an internet connection on a computer. And with us here today to explain the experiment and how it relates to fusion energy are, first of all, from the Office of Communications at the Plasma Lab, Jean Jackson-DeVoe. Jean will be working behind the scenes today to manipulate the experiment while we get an explanation from Dr. Arturo Dominguez out of the lab. It is Arturo who developed the RDGX experiment. And Arturo, let's start, if you could please, by explaining to us just what a plasma is, what it has to do with fusion energy, and the experiment.
All right. Thanks, Dan. So I'm sitting here in the Science Education Department teaching lab at the Princeton Plasma Physics Lab, and behind me I have the RDGX. It's got the shroud on it, but I'll open it up in a little while. So as the name says, Princeton Plasma Physics Lab, we deal with plasma physics, right? So what is plasma? Plasma is the fourth state of matter, right? We have solid, liquid, gas, and when you heat gas up a lot more, you get plasma, right? And plasma is qualitatively different than gas because, among other things, it reacts to both electric and magnetic fields, right? And that's really important, and I'll show you why in a second. So why don't we go ahead and I'll unveil the RDGX for you. Right. So we keep it veiled so that we can actually work in this lab while this is running, because we want to keep it dark so you can really see the plasma once you're at home manipulating it, right? So so this is the setup. What you see is a glass tube that just has air in it, just normal air, but it's held under very low vacuum. It's held at pressures of 10 millitorr to 1,000 millitorr, and that's equivalent to about a millionth of the pressure of the atmospheric pressure to about 1,000th, right? So it's very low pressure, but it's just normal air, nitrogen and oxygen. We put at the ends you see two metal plates, and those are electrodes, and you can put a very high voltage between those two plates. And by high voltage, we mean between 0 to about 2,000 volts between the plates. And that's what's actually going to energize the gas inside and turn it into this fourth state of matter, plasma. And you'll be able to see it. We also have a couple of coils, electromagnets, those red coils around it. And that creates a magnetic field right down the middle. And we'll see how that interacts with the plasma. So why don't we go to the, so right now this is an experiment that has been reproduced many times in plasma physics, in plasma labs all around the world. But the innovative thing about this one is that we've created a website, which, by the way, the link, you guys have access to the link in the details of this Google Hangout session, but it's a public URL. And Jean is actually already connected to it. So why don't we take a look at Jean's screen? And she's already connected to it. And as you can see in the top, you have the video, the live video streaming of the experiment itself. So I'll show you that it's live. Let me put my fingers right there in front, and you should be able to see the video of it. Yeah, there you go. Okay. So it's there, it's live, and what we're going to do is we're going to control it. So Jean is already signed up to it, and you can see her name on the right with 42 minutes remaining because we've reserved this hour slot to show it. And by the way, Princeton, I mean, teachers all around the world, if you want to, for example, show it in your classroom, you can email us and we can do a reservation for an hour or two while you show it. But the typical user can just sign up, and they have 10 minutes to manipulate it and to play with the plasma itself. So you've got the video, you've got the set of controls. On the right, you've got the queue system, in which Jean right now is the first one in the queue. By the way, let me take this opportunity to say that this queue system was initially developed by 2 high school interns here at PPPL, and a lot of what we're going to see and what the upgrades to this system will and have been done and will be done by both undergraduate, high school, and graduate interns. So that's something we're really proud of here at PPPL. On the left, you see some tabs with some supplemental information, and that's effectively a Plasma 101 course that you can follow to really understand what you're doing, what you're seeing, and how plasma is relevant, not only for fusion, but for a whole bunch of other topics. Okay, so let's get to it. Jean, why don't we turn the light off, right? And we see both in my lab that the light has turned off. Jean, why don't you reload the video, because it looks like there's some lag. By the way, depending on your connection, you can get a little bit more lag or less lag, but there's a reload video button right there so you can see it. Yeah, Jean, so you're turning up the voltage. Turn it up to the top. Good. So there, we've put a voltage of 2,000 volts between the ends of it, and we've turned the gas inside into the plasma, right? What else can we do? Okay, so turn on the light for a second, Jean. Okay, so again, the 2 red coils are electromagnets. So why don't we go to the controls supplemental part, the tab, yeah? And let's go to electromagnets. Good. So this is one part of the supplemental information where you have a brief review of what magnets and electromagnets do and how they work. And there you see a diagram of the 2 Helmholtz coils, that's the name of this specific electromagnetic configuration, and the magnetic fields that arise through it, right? Now, why don't we turn on the magnetic fields? Let's go up to the controls. And good. Now let's turn off the light. And let's turn on the magnetic fields up to the top. Great. So you see what happens. Once we turn on the magnetic fields, the magnets squeeze the plasma. So let's see if we can explain why this happens. Let's go to tasks and see what's going on. What does the electromagnet do to the plasma? Yes, let's do that. So first of all, it describes how you get to that condition. And then let's go, yes, let's stay right there. Jean, just a little bit higher up. No, there we go. And so the plasma is made out of ionized gas. So it's both positive ions and electrons. And it turns out that these charged particles spiral around the magnetic fields and get effectively trapped. Really, the magnetic fields grab the plasma and confine it to the fields. So we see the magnetic configuration of the Helmholtz coils, and now the plasma makes sense. What the plasma is doing is it's being stuck on the magnetic fields, and then that squeezes the plasma. Now we know of another example of this happening. Why don't we go down? Keep on going down the page. Well, we know that this happens on Earth. Many of you know that the northern lights, the aurora borealis, are plasma, and the sun is also made out of plasma. So every once in a while, the sun spews out plasma in all directions, some of which goes towards the Earth, right? And now, since the Earth is really like a bar magnet, right, with magnetic fields like those blue lines that you see in that schematic, the plasma comes to the Earth and gets stuck on the magnetic fields and goes to the very north and the south pole. And when it interacts with the atmosphere, it creates the light shows that we know and love, which are the aurora borealis. And actually, in the South Pole, it's aurora australis. So there you see that the plasma isn't really a gas. It's a completely other state of matter. And we can use these magnetic fields and the control that they give us for our benefit. Now, this really ties in to the reason why we're an energy lab, right? We want to reproduce what's going on in the center of the sun, which is really a very hot ball of plasma. And the way the sun generates energy is that the plasma, which is really protons, they're so fast that they collide and fuse together. And that fusion generates free energy. It liberates energy, right? That's the process that we want to reproduce here on Earth. But we can't do it with gravity, right? So we use the magnetic field. So let's go up to the video again, to the live streaming, right? Higher, right? So right now that plasma, it's relatively really cold. It's about 10,000 degrees Celsius, right? So, or Kelvin. That's for a plasma. That's pretty cold. Now it's very tenuous. That's why we can contain it no problem with the glass. But when we deal with a fusion reactor, with a machine that we actually want to generate energy from, then we need the temperatures to go out to about 10 times that of the center of the sun. Now the center of the sun is like 10 million degrees. We're talking like 15 million degrees. We're talking about 150 million degrees. Now we can't just contain that in a vessel, but the way we can contain it is right there in that experiment that you can control. You can use magnetic fields to squeeze the plasma away from the walls and keep it separated from it so it doesn't get cooled down by the walls or it doesn't melt the walls around it. So in this simple experiment, you can really identify a lot of the physics that is very relevant to what we do in a lab like the PPPL, like Princeton Plasma Physics Lab. Now, why don't we try one more thing? Why don't we Gene, can you turn off the magnetic field? All right, good. All right, and we see again, and just reload the video again because it seems to, yeah, there we go. Okay. So we see that the magnetic field is off again. Now, why don't we let a little more air go into the vessel and increase the pressure? So why don't we increase the pressure? Pow! So we get a different, again, it's a plasma, but it's in a different regime of the plasma. And you see it also behind me in the apparatus. And that's very high pressure. And you can see, take it to the top, take it to the maximum pressure, Gene. You can see that if the pressure is too high, the plasma seems to disappear. We lose the conditions to make a plasma, right? Okay, let's lower the pressure again. There, the plasma appears again. Let's lower it much more. Go down to 0 or 10. This is all in millitors, by the way. And again, once we're done with this, you can sign up and play yourself and play with the conditions. But some interesting things start to appear. Look, for example, at those striations that appear in that plasma. Now, some very interesting physics has been shown about those waves. They're called ionization waves, and instead of having like a simulation in which you put in the equations and a video shows up with it, we can actually physically see what's going on here in an experiment. And this is great. This is, anywhere around the world you can view it. Dan, do you have any questions? I've been just speaking like crazy. Dan, have you?
No. And again, anyone can do this. And I wanted to assure people that by sitting at their keyboard on the west coast of California, of the United States in California, no one is in any danger of blowing anything up or getting any shock. This is a remote experiment, right?
Exactly. So yes, we both you're not in danger, and we're sure we've set up the experiment so that there's no issue here. This is 24 hours a day, 7 days a week, right? And actually we've got some analytics going on with the experiment. We've already had more than 3,700 visitors to the website from 109 countries. And in the U.S., we've had visitors from 49 out of the 50 states, and I won't say which Dakota hasn't connected yet.
And sure, it's a lot of, I would imagine that there are parents and children taking a look at this together, students of all ages. And
of all ages and of all backgrounds, yeah. Yeah, so actually I've heard from scientists here in the lab that they've just gone home and shown it to their kids, and it's a great way to show what they're doing here in the lab. Actually, we showed this at a plasma physics conference, and we had a whole bunch of plasma PhDs playing with it and trying to understand what was going on and trying to analyze it. I mean, it's really an interesting experiment when you can play around with the parameters and see what actually happens. And sometimes the behavior is a bit counterintuitive. And by the way, we're continuously developing this experiment. The next edition will be one that will let any user do an experiment that's very similar to one that we do here for the graduate students, that has to do with what voltage is required to turn on the plasma at different pressures. So we're very excited about what's still coming up. So again, we're very happy that a lot of this has been done by high schoolers and undergraduates that have helped me out with this. And we just really want to use this tool to get, just anybody with, as you said, just a wide range of backgrounds to be able to interact with the plasma and get engaged with what we do here in the lab.
Right. And this is, again, a fairly unusual experiment. It's one of a kind. There are no other. There are a number of national laboratories, but as far as you know, this is the only thing of its kind where someone who's doesn't have a government ID badge can sit down and run the experiment.
Yes, right. So this isn't the first time that you've been able to run an experiment remotely, right? We have in CERN, we have remote controls of the machines. We've had other, actually in tokamak, with tokamak physics, we've had control rooms of a machine. Tokamak is the reactors, the type of fusion reactors one of the types of fusion reactors that we use here. We've had control rooms from far away, but as you said, in those cases you have to be one of the team, very restricted access, because in those cases you can you can break a lot of stuff if you do it incorrectly. Whereas here we've done it so that you can actually play with it, but have control of it.
But as you do the experiment, you can get a sense of what it would be like on a larger scale. And maybe this is a good occasion if you could tell us a little bit more about fusion energy. With the plasma, you'd use that to develop the fusion and recreate that. Recreate the effect of the sun on the Earth, but it would be many times larger. And there is one big international project that the Plasma Lab is involved in the ITER project. Perhaps you could let our audience know about that and how the Plasma Lab is involved.
Yes. So as you're saying, there's a big collaboration an international collaboration called ITER. Which is it's a big reactor, experimental reactor that's being built in Cadarache in the south of France. And the U.S. as well as many different nations, representing more than half the population of the world, including the whole European Union, China, Japan, Korea, India, Russia. I'm probably missing some. We are all together working on the development of this tokamak reactor. And PPPL is also doing its part. We're actually going to be, on top of doing developing some diagnostics and some of the technology for it, we're actually going to be testing the one part of what's called a port plug. It's where some of the diagnostics come in. We're going to be testing that, and it's a humongous piece of equipment, and we're testing it in one of the cells of a tokamak that we used to have here at PPPL called TFTR. Again, a tokamak is one of these big reactors. We're testing the port plugs here at PPPL as part of the collaboration that we are doing with this ITER project. So again, this is the biggest scientific endeavor that's ever been tried, and it's still an experimental reactor, but it's going to be the first time that we are going to be able to get more energy out than we put into the machine by a factor of 10. So we're very excited about that. Yeah.
And that international ITER experiment is something that's we expect is going to come online maybe 10, 15 years from now. So it's conceivable that someone manipulating this experiment, some high school student who's interested in physics or in finding clean, reliable energy for the world, could be playing with this experiment today and could find him or herself in a few years after a lot of study, after maybe achieving a doctorate as you did, Arturo. They could be working side by side with you in the lab.
Yeah, no, completely. I think hope that would be fantastic if this experiment helped convince a high school student of how cool plasma physics is and the prospect of getting fusion energy into the future of energy sources. That'd be great. Because as you said, fusion is a very clean and very abundant energy source, because what we need is really hydrogen. It's deuterium and tritium, which are isotopes of hydrogen, but it's really hydrogen, the same hydrogen as H2O. So we can actually get the fuel for our reactors from seawater, after processing it a lot, but we can get it from seawater, and the estimates are that once we get fusion online, we have fusion energy. We have the fuel for fusion energy for many hundreds of years. Plus, it's very clean. It generates very short-lived. The little radioactive byproducts is very short-lived, and it can be buried and 20 years later brought up again, and everything is fine. There's no danger of, for example, a chain reaction that could have like a meltdown. We can't have that in fusion, because if we lose control of a fusion plasma, all that happens is that the plasma turns off. Yeah, so it's a really promising energy source, and I'm really happy that I'm part of it.
Great. Well, perhaps Gene, if you could bring up the information on the connection to the experiment. You can reach the experiment at any time. You do have to get in the queue for the experiment, but you should go to www.pppl.gov, that's a .gov address, /RGDX. Again, that's RGDX for Remote Low Discharge Experiment, and Gene will have that on the screen here in a jiffy. Again, it's free. If you are a teacher and have a class, a science class, or a class of any interest that wants to try this out, you can contact Arturo and reserve time on the experiment.
Right. Instructions are there on the website, by the way.
Right, Arturo. Any last words about the experiment, or to our listeners and viewers?
No, I hope we get a good bump. Stay, keep reloading it and playing with it, because Soon we'll have some more upgrades for it, and as I said, we'll try to get some more parameters that you can control with it. Take a look at the information. Even if you are not controlling it right away, all the supplemental information on the left, you can with it just effectively do a very superficial plasma course, and then there's other links for more in-depth plasma courses if you like. And I think that's it.
Oh, and we should make clear that this is not viewable via a mobile phone. You do have to have a laptop or a desktop.
Okay. Yes. So actually I forgot to say that. So again, as I had mentioned before, from anywhere around the world you can do it, but in order to get a good video connection and everything to be well, you have to have a broadband connection, and you have to download Silverlight. At this moment, we're trying to get rid of that, but at this moment we need Silverlight to operate. So that requires for you to be in a Mac or a PC computer and not a laptop or a mobile device. Nonetheless, actually, if you go with a tablet and go in, you won't see the video or the controls, but you can still see all the supplemental stuff. So, if you're just interested in looking at that. But for now, just go into the using a PC or a Mac with Silverlight downloaded, which is, by the way, what you use to watch Netflix. So it's pretty accessible. You can play around with it.
Great. Arturo, thank you very much for the inspiring demonstration. Gene, we thank you for being behind the curtain and keeping the experiment going. For those of you, again, who are interested in running this experiment, go to www.pppl.gov/RDGX. You can do it anytime, from any place. We hope it inspires you to think more about science and the prospects of clean, reliable energy from plasma physics. We thank you for joining us. Look for more Princeton Conversations on Google Hangouts on Air. Thanks again, and good day.